Yeah, next topic is electrogravimetry. This technique is very useful to determine the amount of species that is by measuring the weight change. Okay. Um, okay. Yeah. Let's continue. This is the analyte is quantitatively deposited on the electrode, and the electrode is measured before and after the experiment, and then from the increase in mass, usually mass is increased, okay, because something is deposited on the electrode surface. Yeah. But if electrode itself undergoes electrochemical reaction, for example, the metal electrode may change their weight by uh, being oxidized, okay. But that's not the usual case. But usually, measure the electrode weight before, after the experiment, and but we have to, we have to determine at which point the reaction is complete. Okay, there are several ways to to know the you know when the reaction is completed. Okay, first the disappearance of color. Yeah, by the color change, yeah, we can decide when to stop, and also whether it is possible to have deposition on the electric surface, freshly deposited, exposed to solution, and qualitative test for light in solution. Yeah, there are several ways, okay, and here your textbook suggests not the determining the end point, also electrochemically. Okay, let's look at this electrochemical setup. Very simple. You take two electrodes, okay, but actually you'll see the two electrode system is not good for the quantitative experiment. Yeah, here I explained rather in detail why we need the three electrochemical system. Okay, reference here, and this is working, and auxiliary or counter electrode. Okay, you will see it vividly. The uh, the drawback of two electrode system. Anyway, let's continue with this two electrode system. Here, you need two electrodes. Yeah. In this case, one is the platinum spiral anode, okay, in a spiral shape. Why? Because to increase the surface area with the platinum, and the other electrode is platinum gold cathode, okay. Um, this is gold type, and the um, people manufactured these types of large surface platinum electrode. This is really expensive. With platinum they made this type of electrode. Okay, and now you put your analyzed solution here in a beaker, and you apply the usually voltage. Okay, um, but sometimes you can apply the current, but when you do the experiment with current, you have to precisely decide when to stop. Okay, so with now simply let's do with this power supply. Okay, then you measure this the current flowing uh, between these two electrodes. Okay, here now this plus end of power supply is connected to this spiral. Okay, so this now platinum spiral is working as a anode. Okay, in the meantime, the negative terminal of the power supply is connected to the platinum gauge, so this platinum gauge is working as what a cathode. Okay, all right, and yeah, this is again it shows the this electrochemical setup, and here our example is to reduce copper uh, ion to copper metal on the platinum surface. Okay, and then we monitor potential the current change with respect to the applied voltage. Okay, usually in electrogravimetry, you apply the constant voltage, but in this case, for the sake of the teaching, um, the this figure shows the current change as a function of applied voltage. Okay, and theoretically, this broken line. Yeah, we expect this kind of the line. Yeah, why? Mm, because when you apply more and more voltage and more current flows, yeah, through this this cell between the anode and cathode, and so the solution has an resistance value, okay, R. Okay, so this is a slope. It shows the resistance. Okay, so we expect, yeah, this is a kind of a naive expectation, yeah, from our very simple knowledge of electrochemistry, and then we expect to get this straight line, but actually this one, this blue curve is what we obtain. Okay, and here from this position, I think this is a minus 0.911 volt. Okay, we already calculated, yeah, in a previous slides, and then starting from here, and then now current we can expect, yeah, when we drive the potential more negatively. Okay, but this one never is obtained, but rather this blue curve is obtained. Yeah? So about minus 2 volt, although you apply more and more voltage, yeah, nothing will happen. Yeah, nothing seems to happen. Okay, there is a very small current, and then beyond 2 volt, about 2 volt, and then when you increase the voltage, then the current began to increase linearly with voltage, and then about at 4.6 volt, and then there is a much large increase in current, when you increase small amount of voltage. Why is that? Why do we usually get this type of curve instead of this straight line? Yeah? Okay, uh, and okay, well, let's treat this one. This one first. Large increase, sudden large increase in current with a small increase in voltage. Why? This one is that is known to be a hydrogen gas evolution. Okay, when you drive the voltage, very negatively. Okay, there is this, since we are working in an aqueous solution, it contains a lot of protons. Okay, and then when you drive potential more negative and negative, more and more. Okay, and then proton is reduced to hydrogen gas. Okay, this is hydrogen evolution, and current will be very large. Okay, and then now question is that what's this small current, and then why from about 2 volt, minus 2 volt to minus 4.6 volt, why the current is more or less linearly increase with the voltage. Okay, that's our question. Okay, okay. And uh, there's a small here current uh, is uh, due to the other things. Okay, uh, probably is the action or potential, yeah, at the anode. Okay, okay. uh, yeah, let me recall this important equation. Okay, although we applied the voltage, constant voltage between the cathode and anode, and since it has, our electrochemical system has IR drop. Okay, and over potentials. Okay, there are several types of over potentials. Yeah, that's why, and we get this kind of the current curve. Okay, because of over potential. This is called the residual current. Okay, and this is due to the over potential. at the anode or at the cathode. Okay, either electrodes. Okay, and but here is the very serious problem, yeah, in this two electrode system, which is here. Let's suppose you hold the uh, the applied potential at the -2 volt. Okay, here. Yes, this is our, simply you applied constant voltage between this anode and cathode, yeah? And let's say that is -2 volt. Okay, and then as copper ion is used up, the current decreases. Okay, here anyway, now you apply this much of voltage, and then copper ion begin to reduce to copper, yeah, at, at the cathode. Okay, not anode, because this is reduction, and then copper ion in the solution, the concentration begin to decrease. Okay, begin to decrease, and then this platinum gold cathode, yeah, this weight begin to increase by the amount of copper deposition. Okay. Mm, okay, so as the copper ion concentration is used up, is a bit decreased, and I decreases. Why? Because the current is proportional to the analyte concentration. Okay, so I decreases. So here, look at that. This is IR drop, yeah, ohmic drop. R is, let's say, this is constant. Okay, system, this R, this R is the solution resistance, or it is also called the internal resistance. This is constant, but I decreases, and IR drop will be decreased. Okay, and then let's assume that over potentials are maintained constant. Okay, and this is all the time constant because we apply the constant voltage. And then what will happen? Yeah, IR decreases. Okay, so to compensate this IR decrease, something, cathode potential or anode potential must change. But what reaction is taking place at the anode? Yeah, anode here are water oxidation, okay, to oxygen gas, oxygen molecule. So since there are a lot of oxygen molecules, okay, so over potential, anode potential may be uh, maintained constant, but only the electrode whose potential is changed is cathode potential. All right, because yeah, we intentionally we applied constant voltage. Okay, so at first the cathode voltage, let's say it is maintained at about plus 0.3, maybe something. Okay, maybe 0.3, 2 volt. Okay, 1 volt. Okay, but as the anode voltage, I'm sorry, this current decreases. Okay, and then to compensate that decrease, okay, decreased amount, cathode voltage decreases to more and more negative voltage. Okay, so this figure shows cathode potential variation with respect to time. Okay, although apparently the total voltage, the applied voltage is constant. Okay, but cathode voltage is changes. Okay, here from at this voltage, and as time goes on, and this decreases, and then this decreases will be a lot. Okay, at first, decrease amount is small, but beyond a certain time, and it decreases very rapidly. Okay, all right. So here, cathode potential falls from 0.3 volt to even to minus 0.4 volt. Okay, so this change is about zero point 0.7 volt. That zero point 0.7 volt is really a lot, really great. Okay, certainly this is not what you want. Okay, this situation you surely want to. Okay, so um, so the now we have to fix this situation. How to maintain this cathode voltage at a constant voltage, okay, mm, regardless of this current change, okay. But before this three electrode system, before this three electrode system was invented, people did the other way, which is to add depolarizer like nitrate, okay, to prevent this type of potential change of one electrode. In this case, that is a cathode. Okay. Okay. Let's what will happen when you add this nitrate ion, okay, into the system. And then when you add a nitrate ion, and then this cathode potential can be maintained more or less at constant value. Why? Because the reduction. Okay. Let's see this one. Current drops, and then in most cases this one cathode may be should potential must drop, but the current is maintained more or less at a constant current by the reduction of a nitrate. Okay, nitrate. At first, the copper ion will be reduced, and then this nitrate ion will pick up. Okay. Mm. So this reaction takes place. Mm. That's how this one the cathode potential in this case can be maintained at constant. Okay, that's the beauty of that's the problem of two electrode system, and to avoid this kind of potential change, you need to do something else. But that doesn't uh, uh, all the time working. Okay, so the complete remediation for this phenomena is to use this three electrode system. Yeah, using this three electrode electrochemical setup. Yeah, you don't need to worry about the change in potentials cathode or anode, maybe this working electrode. Okay, so in electrochemical experiments are being done with this three electrode cell, okay, not two electrode, yeah, except for the several exceptional cases, okay. Yeah, so this three electrode system, this experiment is possible, made possible by this potential stat, okay. All right. Yeah, here is an example. Controlled potential electrolysis. Okay. The question is what the cathode potential is required to reduce the 99.99% of 0.1 molar copper ion to copper metal. Okay. And second question is it possible to remove copper ion to without reducing uh, this one 0.1 molar stannous ion in the same solution. Okay. Uh, this is not about the this potential change problem, but simply uh, we calculate whether we can reduce this copper ion without reducing this stannous ion. Okay, so the first step we have to do is to look up the this HEP reaction, the potential. Okay, for the copper ion reduction, the E0 value is 0.339 volt. But in the meantime, stannous ion, this E0 is minus 0.141 volt. From here, which ion, copper, cupric, or stannous ion, which ion is readily reduced? Since this one, copper ion reduction, this E0 value is much uh, more positive than this one. So copper ion, is readily reducible than stannous ion. Okay, so you can think this way. For the reduction, you apply the negative potential. Okay, so more or less negative potential application means that the ion is more readily reduced. Okay, here, so copper ion is much more readily reduced than this one. But now question is that you want to remove copper ion to copper mineral, how much? By 99.99%. But condition is that the stannous ion, this one will not be reduced. Okay. So let's first calculate the cathode potential. Okay. After the reduction, this much. Okay. And what will be the remaining copper ion concentration? So 99, 100 minus 99.99 is 0.01%, which is 0 10 to minus 4 you know what is a copper ion. So the remaining, after this amount of reduction, remaining copper ion concentration is what? 0.1 multiplied by 10 to minus 4, which is 1.0 times 10 to minus 5. Okay, and then we are using Nernst equation. We calculate electrode potential. Okay, here this is a simple Nernst equation, and then we get this cathode potential is 0.19 volt. Okay, here. So now the question is that at this voltage, whether this stannous ion will be reduced or not. Okay, and then let's calculate uh, the potential, cathode potential. Okay, with this stannous ion concentration. Okay, using Nernst equation, we get E equals, okay, here in this case, yeah, we get minus 0.17 volt. Okay, so this 0.19 volt is still more positive than this one. Okay, so we can safely conclude that oh this one, the stannous ion will not be reduced to stannic. uh, okay, when we remove 99.99% of copper ion. Okay, yeah. So reduction of this much of copper ion without reducing stannous ion appears feasible. Okay, and this is a very simple question. Okay, let's temporarily stop here.